Let's say I want to send you a message that is the four numbers 1, -2, 3, and 5. If I just send these numbers, one of them could get corrupted in transmission, and you wouldn't know that an error had occurred or which digit was wrong. So before I send the message, we come up with a plan. First, instead of sending you 4 numbers, I will send 6. The first 4 are my actual message, and the last 2, A and B, will help you check if there were any errors. Now, I want you to treat these 6 numbers as the coefficients of a degree 5 polynomial, and I will pick the values of A and B so that this polynomial could also be written in the form of a degree 3 polynomial, call it Q of x, times x minus 1, x minus 2. Now we can set these last 2 terms to be x minus any number, but for simplicity, let's say we pick 1 and 2. That way, when you receive my polynomial, you know that if you plug in x equals 1 or x equals 2, you should get 0 for both, because that's how I constructed the polynomial. And if you don't get 0, you know there has been an error in transmission. They are called syndromes, which is an apt term, since syndromes are defined as a group of signs that occur together and characterize a particular abnormality. If the message polynomial is not 0 at any of the syndrome values, then there is an error in the code. So how do I find the values of A and B in our example? Well, I take the polynomial without A and B and divide it by x minus 1, x minus 2. I get a degree 3 polynomial, which is what I want, but there is also a remainder of 37x minus 30. So I can move this to the left-hand side. For the polynomial to take the form I want, A must be negative 37 and B positive 30. So I send the message 1, -2, 3, 5, -37, and 30. You can plug in x equals 1 and x equals 2, and if you get 0 for both, you know the message was sent correctly. But what if there was an error in transmission? Say at position 4, the number has changed to a 6. Well, now if you evaluate at x equals 1 and 2, the polynomial is no longer 0. To figure out where the error occurred, one at a time, you set each coefficient to be a variable. Then find the value of that variable, setting the polynomial equal to 0 at x equals 1. You repeat this for x equals 2. And what you find is that the 2 values are different. This indicates that the second coefficient was not the error. You find the same for all the other coefficients, except when you reach the one where the error occurred. Here, not only are the 2 values equal, they are also equal to the originally transmitted number, that is 5. So this method allows us both to check and correct errors with only a modest increase in data size. Reed-Solomon encoding uses finite field arithmetic, Galois fields, to obtain the error correcting terms. These converted back into binary are